is Julia Hartmann from the University of Pennsylvania, and she'll talk about local global principle for constant reductive groups over arithmetic function fields. Please go ahead.
Everybody, much the introduction and for the opportunity to speak here. So those of you who go to this seminar regularly heard a talk by Danny Krashen last spring, so not quite a year ago. That's somewhat related to what I'm talking about today. Danny was mostly talking about the case of tori. He was mentioning the reductive groups at the end. That was work in progress at the time, whereas the tori paper was already on the archive. Now we're to the point where this is getting very close to being put on the archive. I hope I'm not saying too much. And I'll take a slightly different viewpoint also. So there should still be lots of new stuff. So local global principles we all know and love, and we know that classically, when we're looking at local global principles for algebraic objects, then we can often instead look at local global principles for homogeneous spaces under linear algebraic groups, and there the most important case is the case of torsors. And so we can phrase this in terms of Galois cohomology, and then we'll say that a local global principle for G torsors holds. Well, so this is if and only if I map from the cohomology of F, so G is a linear algebraic group over F, and I map to the product, and here classically you would take all the, if F is a number field, you would take all the completions at places, and then if the kernel of this is trivial. But we of course know that often it isn't trivial, and so we can give this kernel a name, and that will be the abstraction to a local global principle, and so that's what we're going to study. So let me just say again, so here maybe F is a number field, and then these are the places, and these are the completions. So let me remind you of a couple of known results just to over number fields or over global fields more generally, just to put things into context later. So over global fields, a few things that are known. This is not a complete list, but the things that I'm interested in for today is if G is semi-simple, simply connected, then this abstraction vanishes. And so this is due to Kneser, Harder, and Chernusov. And then similarly, if G is connected and rational, and F is a number field, then this abstraction also vanishes. And this is, I believe, due to Sansuk and Chernusov. And then if we don't know anything else, then at least we can say that this abstraction set is always finite. In the number field case, that was due to Borel and Serre, and then more recently, Brian Conrad showed this in the function field case as well. So today, we're going to work over semi-global fields. These are the arithmetic function fields that I had here in the title. So that's just a different word, which I hope, in the title, you maybe have some idea of what that might mean, some intuitive idea. So what is this going to be? Let me introduce some standing notation. So what is a semi-global field? F over a field K. So this is a one variable function field, F, over a complete discretely valued field K. So what do I mean by one variable function field? So first of all, it's finitely generated, transcendence degree 1, and included in that definition, I'm also going to assume that K is algebraically closed in F, if I'm saying it's a function field over K. And of course, otherwise we could replace K by the algebraic closure of K and F, and then it would still be a semi-global field just over that new field. So more standing notation, R and K will be the valuation ring. T will be the uniformizer, and little k will be the residue field. And then we're going to pick what we call a normal model of f over r. So this is going to be a flat projective integral R scheme with function field f, which is normal as a variety. And we're going to assume, so we will assume, not just we may, but we can always get there, that it's reduced closed fiber. So we're base changing it to the residue field. Is a union of regular curves with simple normal crossings and intersections. And we know that that can always be achieved. Now, if we think about these local global principles, so let me go back to where I wrote this at first. If you think about these more generally, then really what we were considering in a way is just a field f. And then instead of going over the places, we could have just considered a collection of overfields. So these could be maybe any kind of fields L coming from some set of overfields. And the thing about these, and then for each of these collections, you get a potential local global principle, and for each of these collections, you get an obstruction. And so the thing about these semi-global fields is that they naturally admit several such collections of overfields that are motivated from geometry. And so for each of them, like I said, you can ask, does the local global principle hold? And what is, if not, what is the obstruction? So let me explain what these look like for a semi-global field. And many of you have seen this before, but because I need the notation, I still have to go through it quickly. So for each P in the closed fiber, we can define a field and a ring, of which this is the fraction field. And so what is this ring going to be? Well, this is just going to be the complete local ring at P. And so then we get a collection of overfields of this form. So I do this for all points of the closed fiber, not just the closed points. And then if I have such a collection, I get a corresponding obstruction to a local global principle. So this will be the kernel where I map to all the L in omega x. And again, G is a linear algebraic group over F. So that's the first collection of overfields I get naturally for a semi-global field once I've picked a model. Another one, actually many other ones, are coming from what we call patches. So we pick a non-empty finite set of closed points of X, and we want them to include all intersection points of components, and also at least one point on every component. So then we're going to let U be the set of components of the complement. And then for an element in there, we also have an associated ring and a field. So we let RU hat be the t-adic completion of the set of elements in F that are regular along U. And then we let FU be its fraction field. So now we have these finitely many points P. For those, we have previously defined associated fields FP. And now we also have these finitely many components, and we've associated fields to them. So we get a new collection, which I call omega subscript P, which is just the collection of all of these. So I'm taking these finitely many FPs and the finitely many FUs, and that gives me a collection of fields, and it's a finite collection. And notice this depends on the choice of this set script P, which I could enlarge, for example, and still have those conditions be met that I put on it. And so I get many, many of these. And then again, I get a corresponding local global map, and I get a corresponding obstruction. And the first fact that makes this a little bit interesting, hopefully, is that these obstruction sets aren't unrelated. Namely, in general, we know that they are contained in one another. And so in particular, if I'm going to study the sort of the more classical obstruction set where I'm looking at completions with respect to discrete valuations, I can do that to some extent by studying these other local global principles. Now, why is this good? Why is this helpful? Well, so first of all, we noted that for this obstruction set here, this came from a finite collection of overfields. And so there's a combinatorial description of these overfields possible, and that lets us hope that there might be a combinatorial description for the obstruction set. And so here's how that goes. So if P is on the closure of an element U in U, then I have my field F, it's contained in FU and it's contained in FP, but there's actually a common overfield that both of those are contained in. I'm going to denote FUP because it's uniquely defined by U and P. And this is a common overfield, and this is not something that you would expect if you were looking at other types of completions. So this is something special to this situation. And what's this UP? Well, this is a branch. And what does that mean? It's a height 1 prime of RP hat lying over the ideal that defines the closure of U. And then R UP hat, the associated ring, is the UP adic completion of the localization of RP hat at this ideal UP. And then again, as usual, FUP is its fraction field. And it's not so important exactly what this definition is. It's important that it's a common overfield. And the other nice thing about it is that this RUP hat is a complete DVR. And that's something that will play an important role later. And so what does our description look like? This is a theorem that's now 10 years old. And it says that this obstruction set that we're considering can be written as a double coset where you're looking at all these overfields associated to branches, and you're modding out by everything that came from the FUs and everything that came from the FPs, respectively. So this is for all U and U and all P and P, and these are over all the branches. So the pairs U comma P. And in particular, what this says is that any torsor that's trivial locally with respect to this patches set of overfields is represented by a collection of elements so every torsor defining a class in here is represented by some collection of elements GUP in this product. And that's something that we can really work with, and that's very explicit. So one corollary that we get from this, that's also about 10 years old, is that if G is rational over F, not necessarily connected, then this obstruction set can be explicitly described in terms of what is called the reduction graph and the set of components of G. So let me introduce this notation here. So here, gamma is the reduction graph of, so this is associated to, I guess, the closed fiber and the set script P, which determines the set U. And what does it have? It has vertices, the elements P and U, and it has edges for these branches. And the edge UP will connect the vertex U to the vertex P. So notice that this group here, because this is a graph, this is a free group. And so in particular, this abstraction set will be trivial if and only if either that group gamma is trivial, as pi1 of gamma is trivial, which means that gamma is a tree, doesn't have any loops, or G is connected. So in particular, if you go back to the connected case, you see that you actually get a trivial abstraction set. And so if we compare this to what's known in the case over global fields, then we get sort of the analog of this with that modified version of the local global principle. And so the question is, what about the other two results that I told you about before? And so today, what we're going to do is focus on G that is defined over the underlying DVR and is reductive. And so why is that? Well, it was known that by a counterexample of Colliot-Thélène, Parimala, and Suresh, that the local global principle can fail for arbitrary tori. And then at some point we started studying tori that are defined over the valuation ring. And there we could say some more concrete things. And then we went on from there to reductive groups. And for these reductive groups, two nice things happen. So the first one is that if you take a P as above, then these inclusions that I wrote down before between these abstraction sets here, they all become equalities. In this case, where G is defined over R and reductive. So if there were any concerns before that we would only get partial results about kind of the abstraction set that we're really interested in, those are now gone because it really describes this, the patches abstraction is equal to the full abstraction set that we might be interested in. And the second thing is that from work of Harbater, Krashen, and Lieblich, we get an integral version of the double coset description. Right, so here was the double coset description. That was something that is very concrete that one can work with. And because we know that the group is defined over the underlying discrete valuation ring, we actually get an integral version of that. So what does that look like? So if I looked at torsors that are defined over X and become trivial over the corresponding rings for the patches, so those were the RP hats and the RU hats, then those correspond bijectively to double cosets of the following form. So it looks exactly the same as before, except I've replaced all the fields by the rings. So it's sort of an integral version of that. And so what is this abstraction set here? Of course, this is the kernel. So I said this orally. These are all the torsors over X that become trivial locally everywhere over the RUs, RU hats, and the RP hats. So we have two really good things to work with. And so for now and for the rest of the talk, I want to assume that the characteristic of our residue field is 0. Why? Well, we have stronger results in that case, and also certain hypotheses are easier to state. I'll try to remember to make remarks in each case to say what happens if you're over a field of more general characteristic. So one of the key tools here is to actually work with this double coset description that we gave and do something with it in this particular case that we have a reductive group defined over the valuation ring. And so we want to take our double coset representing a torsor and we want to tweak it. And so here's the proposition. So we're going to assume that this reduction graph gamma is a geometric tree. And what does that mean? It means it stays a tree even if you base change your field to a finite extension. And so if we have a collection of elements, so this is a collection representing a torsor, so there's one for each pair UP, then what this proposition says is that we can modify this, and we can modify this to stay in the same double coset. So remember, I can modify it on the left by elements in G of FU, and I can modify it on the right by elements in G of FP. So this is for all U, and I also get elements for all P. And so that what happens? So that if I look at the corresponding products, right? So if I take that collection, it's a collection that represents the same torsor in that double coset description. So this is now better than before in two ways. So one way is that it becomes integral. So I've gone from these elements being defined over the field FUP to them being defined over the underlying ring. And now it makes sense to reduce it modulo the ideal UP, and it reduces to the identity. So this is for all such pairs UP. And I just want to give you sort of the very basic idea of the proof, just so you see a little bit of the ingredients, because those will become important later. So we know that this gamma is a geometric tree. So that means we can start with a root of gamma and do induction. And so without loss of generality, under these assumptions, one can show that we can always assume that the root is one of these sets U. Remember, all the vertices in the graph, they were either U's or P's. I'm going to draw a picture in a second. And then we can assume that the root is one of these sets U. And so we can now proceed by induction on the distance of a vertex from this root. So we can assume that it's okay for a distance at most 2n, where for n equals 0, we have to define what this element is associated to the root, and we're just going to set that to be the identity. And so in the induction step, we have to deal with the distance 2n plus 1 and the distance 2n plus 2. So because we started out with an open set in U and U, at an odd distance from that, there'll always be a point. So this will be a point. And then at the next even distance, there'll be another U. And this only happens if P is one of our intersection points. So P is a singular point, because otherwise it only is on one component, and then that corresponds to a leaf of the tree and nothing else happened. There's nothing further out, further distance. So let's focus on that case. So what does this look like in our closed fiber? So we have the point P, and we have these two components, maybe U and U prime. And what does this look like in the reduction graph? So we said for P and for U and for U prime, we get vertices. And so this U is somehow the vertex that's closer to U naught. So we've already dealt with that one. So we've already defined. G sub u, and we want to define G sub p and G sub u prime. And notice that the G sub p is special because it needs to work for both of those branches, right? These are the two branches here. These are the two branches. And I'm only going to get to pick that element G sub p here once, and it needs to work for both of those. Okay, so how do we do that? And the main tool here is that assumption on our reduction graph, namely locally at the point P, if I take a maximal split torus over the residue field of P, that lifts to a maximal split torus S that's defined on some open subset W in U prime union P. So I'm taking this component U prime, but I'm adding in the point P, and the W is also supposed to contain the point P. And so we can sort of extend that torus. And the reason why that works is this monotonic tree, the geometric tree assumption, which Danny in his talk, if you remember his talk, he was talking about monotonic trees and characteristic 0. Those things are the same. And the principle here is that if you move away from the root, the residue fields cannot get any smaller. They can only go up. And what does this allow us to do? It allows us to reduce to the anisotropic case. And in the anisotropic case, we know by work of J.L. that if I look at the rational points over my field, sorry, the field doesn't get ahead, over my field, remember that was the fraction field of a complete discretely valued ring, because that's what these branches are. So that's going to be the same as the R hat rational points. And so that will allow us to get into, to modify things to get into this sort of the integral point. So for anisotropic, they would be the same. And we're doing this sort of locally, we're able to get into that anisotropic part. And so therefore into the integral points. But then similarly, if I look at what I get here, if I mod out by the ideal UP, then that will also be the same as if I took our P hat and modded out by that ideal. That's again because this is going to be a complete discretely valued ring, and this is going to be its fraction field. So by the same token, I get that these two are the same. And so that means I can adjust things by elements in RP to get them to be trivial module of the ideal UP. So that's the main tool in there and the basic idea. And notice that the rank of the maximal split tori will vary or can vary as we move through this graph. So they're not always the same. So there's no chance to do this sort of globally. So we have to do it locally. Now, corollary, in the case where the closed fiber is reduced of my model, and then gamma and G are as above. So gamma is one of these geometric trees, and Z is a G torsor whose class is in SHA, so it's locally trivial. Then this Z extends to a G torsor over the model, which is trivial when reduced to the closed fiber. So why is that? Well, we know that our element of SHA is an element in SHA P. That's this fact up here. Right, so that therefore we know it corresponds to double coset. And we've just modified that double coset to actually lie in here. That's what the proposition did. And it modifies it to lie in this integral double coset description. So therefore, it corresponds to a torsor over X that is locally trivial. And because we made everything so that it reduces to the trivial thing on the closed fiber, this torsor becomes trivial on the closed fiber. And so then as an immediate consequence of that, using work of J.L and Parimala and Suresh, is that if G is reductive over R as before, and gamma is a geometric tree, then SHA is actually trivial. So the work of J.L, Parimala, and Suresh going in there is the statement that if you have a torsor as in that corollary, so a torsor over X, which is locally trivial, so trivial when reduced to the closed fiber, it's actually trivial. So we reduced to their result. And in characteristic 0, where we are, you can do a little bit more. So let me say first, in general characteristic, for that result, you need mild hypothesis on G. So you need it to behave well. So you need, yeah. And you need a condition on the algebraic fundamental group of the group, but it's a mild condition. But in our case, where we are at characteristic 0, you can get even more. You can get this for any connected group over R.
Julia, sorry. Do you hear me?
Yes, I hear you.
Okay, good. So in our theorem, so there are some very small restriction of characteristics. So you
right.
So
that's what I was saying.
Okay, good.
So there are some small restrictions in the characteristic in general, and because I didn't want to state them, I'm just writing things down for characteristic 0. And I think your assumptions in characteristic 0 are always satisfying.
Of course, in characteristic 0, everything works. Yeah.
Right.
Thank you.
Okay, but yeah, it works under mild hypothesis on the, well, I mean, if you fix the characteristic, then it's a hypothesis on the group, or otherwise it's a hypothesis on the characteristic, right? So, okay, so that's the case of these nice trees that remain trees when you base change the residue field. What if we're in a more general situation? So the main thing that we were doing was to reduce to the anisotropic case. That was the main tool in that proof, and that will not work if you don't have this assumption on the residue fields, and you can't lift a maximal split torus. And then this approach, in the sort of the naive way, no longer works. But if you have a reductive group over a complete DVR A with fraction field L, and let's say residue field little l, then right before we were able to somehow go from G of L to G of little l. And we can't do that anymore, but we can do something that serves as a replacement for that. So we can go from G of A, obviously, to the fraction field and to the residue field. And we would like to go sort of here. And for anisotropic, that works, but in general, it doesn't. But what does work is that if you go over to R equivalence, then you indeed get a map here that makes that diagram commute. So, and this is even surjective, because this is surjective by the smoothness of G and the completeness of A. So what this gives us in our situation specialization maps. So we're kind of using this twice. So first of all, we had these nice branch fields. Those are sort of the nicest ones because they were complete discretely valued fields. And so there you can go all the way down to the residue field, which is the same by definition as the residue field at the point. Similarly, you can do this over the FPs via going to the completions, and you can show that the two different choices that you have there, sort of where you complete first, it doesn't matter. So they agree. So here you can go down to the residue field, mod R. And so these are the same. And then what about the FUs? Can you specialize there? Well, so yes, there is a specialization map where you go via the generic point of that component that you had, and you get to K of U, G of K of U mod R, and that then maps to here. And the thing that I'm going to talk about today is a special case of this, namely if this U is contained in some copy of P1, then this becomes surjective, and then this is actually the same as G of K. Well, so the residue field of U, so kappa of U, I guess I should say. Mod R. So these are all the residue fields here. So for the component, those are the constants in the function field of the component. And for the branch, it's just the residue field at the point. And so from that, we then get the following theorem that if the closed fiber is reduced, because that's what we needed for our patching setup, and is the union of P1s meeting at K rational points, then we get an explicit description via the residue fields. And so we're again taking products over the branches, over the P's, and over the U's. But you notice now that in this description, all the groups are actually the same. So it's just a question of how the groups for the various different P's and U's embed into those for the branches. And so you get a completely combinatorial description and one way to write it. And it depends on how these connect. Well, how these connect is encoded in the reduction graph, right? So you get a description that looks like this. And then you have to mod out by simultaneous conjugation, because you have this description in terms of these classes. So that gives a very explicit combinatorial description of the obstruction set in that specific case. Why is that interesting? Well, it lets us get some examples. Let me also note here at this case that if we're in a more general situation where maybe these aren't meeting at K rational points, but at points that are defined over a bigger residue field, you still get a lower bound on the SHA, but you just get the bijection in this particular case. So let me go to the applications. So the first application is that if we take a model for some function field where the closed fiber is a triangle of P1s. It looks like this. So what does that mean for the reduction graph? The reduction graph will be sort of the barycentric subdivision of this. So it'll have a vertex for each of the P's and each of the U's. So it'll look like this hexagon. And you can explicitly give an equation for something like this, and it's similar. I mean, this type of example already came up in the work for of Colliot-Thélène, Parimala, and Suresh when they gave a counterexample for toric. So here we can see we have one loop in the reduction graph. So in particular, pi1 will be non-trivial. And then what our description here says that is as soon as G of K mod R is non-trivial, we will get a non-trivial obstruction set, right? So now if...
So, sorry, Julia,
Yes.
This is example one, you can take a kind of elliptic curve, right?
Yeah, I mean, I can write it down. So you can take, for example, what you take. X, Y, Z, and then you want something that goes away, mod T, and has higher order. So like that, for example.
It's very simple. Yeah. Thank you.
Yeah. Now, if G is any group, well, reductive, right? So that G of K mod R is non-trivial, then our theorem tells us that SHA will be non-trivial. So we just got to go hunting for a group where G of K mod R is non-trivial, and thankfully other people did that before us. So what's known is that if G is SL1D, where D is a K-central division algebra, then G mod R is SK1 of D. That's due to Voskresenski, I believe. And so we only need a non-trivial example for that. And there are examples where this is a power of Z mod 2. So in particular, you can get one where it's Z mod 2Z. And this is an example due to Platonov. And you can write it down very explicitly. So in this case, we would get that SHA FG is 2. So it's non-trivial. So why is this interesting? Well, and noteworthy. So we can get that this is non-trivial even when G is semi-simple, simply connected. And if we go back all the way to the beginning, we see that this is very different from the case, sorry for all the scrolling, very different from the case of number fields or global fields, where the obstruction in that case always vanishes. So we think this was the first known example for a semi-simple, simply connected group where the local global principle fails over a semi-global field. You can also modify this example to make the geometric structure simpler. In a way, the example gets more complicated if you do that. So what you can do is you can replace the closed fiber by something that is actually a tree, but doesn't have this geometric tree hypothesis. So you can have two lines, two P1s, intersecting at a non-K rational point, and then that can happen in such a way that that actually you still get a non-trivial obstruction set here. So that in particular also shows that the additional hypothesis that we had on gamma is actually necessary. So you can't just say it's a tree or something like that. So if it's just a tree but not a geometric tree, then this is not sufficient. Okay, from that, it can get even worse. So remember, if we go back to the global field case, we had three statements here. The first one was for rational connected groups, local global principle holds. That is still true in our situation. G semi-simple simply connected local global principle holds. That's no longer true. But what about the finiteness of SHA? Well, in the paper that Danny reported about, where we were looking at tori over the underlying discrete valuation ring, we already gave examples where this can be infinite, but here you can get it in a case even where the group is semi-simple, simply connected. So the main ingredient here is that if you have G of K mod R is non-trivial, then you can show from that G of K mod R, the map to G of, now you take the function field of G and the points mod R, that is injective, but not surjective. Right, so why is it injective? Under our hypotheses, G is unirational. And so G of K is dense in G. And so that means that if you have any non-empty open U in G, then U of K will be non-empty. And so if you have 2 points, 2 K points that become R equivalent over the function field of G, then they're already R equivalent over some open subset, and then you can specialize to a K point in there to get the R equivalence over K. So that shows that it's injective. And why is it not surjective? Well, I'm only sketching that too. So if it were surjective, then the generic point in G of K of G would be equivalent to something in G of K, right? And one can show that this would imply that G of K mod R is trivial. And that's contradicting our assumption. So now if you know that whenever you go over to the function field of the group, you get a proper inclusion of the R equivalence classes in your group, then you can keep doing that infinitely many times. And so there exists an E over K so that G of E mod R is infinite. And then you can just take that example from before and tweak it so you can let G tilde be SL1 of D, and you tensor with E. So remember our underlying discrete valuation ring, we were in the characteristic 0 case, so it's an equal to characteristic. So it's going to look like power series in the uniformizer. So you can tensor that up. So this is with D as above. So for example, from that Platonov example here, where you get something non-trivial. And then you also got to modify F and base change it up. So you can base change that from the residue field little k to the residue field E in the same way. So F is as above, meaning it's the function field of this curve that had the triangle in the closed fiber. And then we get that the obstruction set is infinite. And again, even though G is still, or G tilde in this case, is still semi-simple simply connected. So if we go back to our list of things that hold over global fields, then the finiteness here also does not hold, not even for semi-simple simply connected groups. Okay. So I'm a little bit faster here than I was planning to be, but I want to make some final remarks. Namely, if we go back to the description of the obstruction set for G rational, but possibly non-connected, then there we had this description where we were looking at hum of pi 1 of gamma and then G mod G naught, right? But in our situation, if G is a rational non-connected group, then G mod G naught is G of R, G mod R, because you know the connected component is rational, so everything there is R equivalent. So this description that we had there can be rewritten in the case that where we are using this R equivalence. And so this theorem that we proved 10 years ago, if you look at it from that point of view, now looks exactly like this description here. And so when we started working on tori at least from my point of view, and I know that some of my collaborators have been working with this R equivalence for much longer, but from my point of view, the R equivalence came in sort of kind of through the back door because we were using these Flask resolutions, and it came in from that point of view. But it seems that maybe this R equivalence is, and I guess that's not surprising because it's connected to rationality, but it seems more intrinsic here in the description, and we're kind of hoping that using it might give more general results or more general descriptions of these abstraction sets that are sort of specializing to the ones that we've been able to show in the past. All right, like I said, I was talking a little bit fast, so that's actually all I wanted to say, and thank you for your attention.
Thank you very much. Are there any questions? Okay, there are no questions. Let's thank.
I have one.
Oh, please.
What happened? What happened if the curves are not P1? I mean.
Okay, if the curves are not P1, then the problem is that this map here does not need to be surjective. And
Yes,
so then, you can sort of, you get a map from here to here and you get a map from there to there, but you don't really get a lower bound from these groups over the residue fields. So there's maybe something more general to be done there, but for now, that's the case that we understand.
Okay, thank you.
Anyone else? Okay, if there are no further questions, let's thank the speaker again.
Thank you.